Hello, everyone. Good morning, good afternoon, good evening. Welcome to our program once again. And today we'll be continuing our series on engineering thermodynamics. So we'll be continuing on our exercises on the first law of thermodynamics. Last time we did our first worked example. Today we'll be continuing. And we're doing a second simple worked example that relates to electricity generation via a steam turbine. Now, this steam turbine might be powered by any source of primary energy. It could be gas, it could be any kind of fuel, it could be even, it could come from a nuclear reactor that raises steam. So regardless of how the steam is raised, the essence of this question is to see how energy is converted from steam to electricity. So here we have high pressure steam coming in to the system. And then when it passes through the turbine blade, of course, there's expansion of the steam and that leads to rotation. And since there's a mechanical coupling between the shaft of the steam turbine and the rotor of the generator rotor, which is essentially a magnetic field, rotates. And we know that by Faraday's law of electromagnetic induction, if there is a relative motion between a magnetic field and a fixed coil, an EMF is induced. When we say EMF, we mean electromotive force, or in simple terms, voltage is induced in the coil. And of course, when the terminals of the coil is connected to a load or to a system down the line, then current flows, and we say power has been generated. So in this question, the question goes this way. In a steam power plant, high pressure steam that is from the source side with an enthalpy of 500 megajoules. By enthalpy, we essentially mean the energy content of the steam. 500 megajoules is supplied to a steam turbine. It converts this thermal energy into 200 megajoules of mechanical work. That's rotation of the shafts. This mechanical work in turn drives an electrical generator to produce 180 megajoules of electrical energy. Now the question goes this way. Calculate, number one, the energy dissipated at heat from turbine low pressure steam that's on the other side. For instance, assuming the steam comes in here and exits from here after doing work, we are trying to find the energy dissipated at heat on this side. That is the exhaust steam after doing work. Two, the turbine efficiency, which is the ratio of the mechanical output to the input heat. The generator efficiency, which is the ratio of the electrical energy generated by the generator to the input mechanical work. Or four, the overall system efficiency. Five, the overall system efficiency if the steam turbine is driven by a gas boiler at 85% efficiency. That is, if it gets its primary energy from gas, where there's another component here, which is the gas boiler that receives energy from gas and converts water, liquid water, to steam as a result of the combustion of the gas. So find the overall system efficiency under that condition. So we move forward. Now here's the turbine, the steam turbine. As the question says, it receives 500 megajoules of energy at the input. And then 200 megajoules of mechanical work which drives the generator through the common shaft. First question says, we should calculate the energy dissipated on the low pressure side of the steam turbine. And we're also told that the generator generates 180 megajoules of electricity. So, by the first law of thermodynamics, there's energy conservation in the heat engine. There's the total energy going in equals the total energy going out. In that case, QS equal to WM, which is the mechanical work, plus QL, which is the energy dissipated on the low pressure side of the steam turbine. So if QS equal to QL plus WM, that means QL becomes QS minus WM, as you see here. So 500 minus 200 gives you 300 joules. So here we have 300 joules. Therefore, the efficiency of the turbine, which is the ratio of the mechanical work output to the heat input, simply becomes 200 over 500, which equals 0.4 or 40%. Similarly, the efficiency of the generator is simply the ratio of the output, which is 180 megajoules of electricity, to the input, 200 megajoules of mechanical work, and that gives you a 90% efficiency. The efficiency of the system, the entire system consisting of the turbine right through to the generator, is the ratio of the output, the overall output of the system to the overall input of the system. That's 180 divided by 500, which is 0.36. A simple way of doing it is simply to multiply the efficiency of each component. So when we have more than one component connected in series in this way, the efficiency of the system is actually the product of the efficiencies of each component. And that's why we see here NCs equal Nturb times N gen. Now this actually not N, this is a Greek letter, but let's just call it N for simplicity. So this is the efficiency of the system from steam to electricity. Now, the next question says, if a gas boiler produces a steam, calculate the overall efficiency. So when a gas boiler produces steam, that means the boiler gives you the steam energy from gas energy. And so we want to calculate the overall efficiency from the gas input down to the electricity generation. And we will say that the system efficiency is a product of the efficiency of each component connected in series. So that means system efficiency is efficiency of the boiler multiplied by the efficiency of the turbine and multiplied by the efficiency of the generator. Putting everything together, 0.85 multiplied by 0.4 multiplied by 0.9 gives you 0.306. That's 30.6% system efficiency. Okay. Now, here's another example, another worked example on the first law of thermodynamics. Can you give a try to this? 40 kilojoules of heat is added to a gas mixture in a cylinder, 1 at constant volume, 2 at constant pressure. Calculate the work done and change in internal energy in each case. Now, let's look at the solution. So the first statement says that the heat supply to the system is 40 kilojoules at constant volume. Constant volume means there's no change in volume. And we know that work is done whenever there is an expansion of the gas. So when there's no expansion, that means work done is zero, essentially. Work is done when there is gas expansion or change of volume. Since there's no expansion, that means dV equals zero. And if dV equals zero and work, from our previous lectures, we see that work is the integral of pressure with respect to volume. So if pressure with respect to volume is zero, then the integral thereof is zero. Therefore, the work done equals zero. And if the work done equals zero, we know that by the first law of thermodynamics, heat supplied is equal to work done plus change in internal energy. And so when work done is zero, for a 40 kilojoules heat supply, that means change internal energy equals 40 minus zero equals to 40 kilojoules. So what this implies is that the entire heat supplied is converted to a change in internal energy. So let's look at the second part of the question. So the second part talks about constant temperature. Constant temperature means delta T equals zero. And when the delta T equals zero, that means there's no change in internal energy. Hence, delta U equals zero. And that simply means that the total heat supplied, Q, is converted to work. Remember, this is not a cyclic process. Now, let's look at another example. 40 kilojoules of heat is added to a gas mixture at initial pressure of 150 kilopascals, leading to expansion from 0.1 meter cube to 0.3 meter cube. Calculate the work done and change in internal energy if, number one, the pressure is held constant, number two, the gas mixture behaves like an ideal gas. Now, we represent the situation in a PV plot, or a plot of pressure, gas pressure, in kilopascals against volume in meter cube. So the first case, we know that in general, from our previous lectures, if you can go back to our previous videos and watch, you will see that the work done for any system is given by the integral of pressure over volume. And since P is constant, by the law of integration, P comes out of the bracket, so it becomes W equal P integral dV. And integral dV from V1 to V2 is simply V2 minus V1. So work is the product of pressure, the constant pressure, and the change in volume. This is essentially the area under this process rectangle. So we have a constant pressure of 150 kilopascal, and then the volume changes from 0.1 meter cubed to 0.3 meter cubed at this constant pressure. The work done is simply pressure, which is essentially the height of this rectangle, multiplied by the base of the rectangle, which is V2 minus V1. That is 0.3 minus 0.1. So work equals 150 times 0.3 minus 0.1 equals 150 times 0.2, and that gives you 30 kilojoules. And by the first law, delta U, which is the change in internal energy, equals heat delivered minus work done. And since heat delivered is 40 kilojoules, becomes 40 minus 30 equals 10 kilojoules. So that's a change in internal energy of the gas in the process. Now, we look at the second part of the question, which says, where the work is done no longer under constant pressure, but under ideal gas behavior. And what is ideal gas behavior? Well, ideal gas behavior is given by the so-called Boyle's law, which states that the product of the pressure and the volume of a gas is constant. That is, PV equals K, which means P1V1 equal to P2V2 equal to P3V3 and so on equals K. And so if PV equals K, that means pressure is not constant but varies with volume by this equation, P equals to K over V. So if P equals to K over V, you slot in K over V into this expression. By substitution, the integral becomes W equals to integral from V1 to V2 K over V dV. Bringing out the constant K, it becomes W equals K dV over V. And we know that when an integral has an expression in this form, dx over x, the integral is natural logarithm of x. So dv over v, the integral is natural logarithm of v and is a definite integral between v1, that's the initial volume, and v2, the final volume. And so it becomes k natural logarithm v2 minus natural logarithm v1. And by the laws of logarithm, log A minus log B is equal to log A over B. So this gives rise to K natural logarithm V2 over V1. But what is the value of K? We'll see in the next slide. K is PV, isn't it? So P1V1 is K, P2V2 is K, P3V3 is K, and so on, depending on the number of changes in volume. So replacing K with P1V1 and substituting, we have W equal 150 times 0.1 times natural logarithm 0.3 divided by 0.1, which eventually leads to work done equals 16.5 kilojoules. And this is, so here we have represented here the work done at constant pressure. But under ideal gas behavior, there's a deviation from constant pressure condition, and we have something like this. An inverse relationship between pressure and volume. So that inverse relationship leads to a reduction in the area under the graph, or a reduction in the work done, because work done is defined as the area under the pressure against volume graph. And that, in essence, corresponds to the answer we got, because initially the work done was 30 kilojoules, but now it's just a little over 50% of that. That's 16.5 kilojoules, which accounts for the fact that the gas is behaving as an ideal gas. Of course, we know that this is closer to how gases behave naturally than isobaric condition. For an isobaric condition, you need actually to supply more energy to work against the pressure or the constant pressure. So the constant pressure is not a natural behavior of the gas, but it's imposed by an external power source. For instance, a motor might maintain uh, the gas at constant pressure, the gas in the piston at constant pressure while the piston is expanding. So you need an external force to do that. And so to overcome that external force, you need more work. And that's why the work done at constant pressure is higher than the work done under normal ideal gas behavior. Okay, I hope these examples are clear. So till I come your way again next time, this is Jay. Thanks for joining us. Remember, we are engineering for the streets, on the streets, and by the streets. Our goal is to democratize engineering. Thank you. Bye for now.